Hey YouTube, what's up? Dr. T here, and welcome to the Altcoin Express and my hometown, St. Petersburg, Florida.
Had predictions of your score on a test based on how... Last time, we built a neural network in Python that made really bad predictions of your score on a test based on how many hours you slept and how many hours you studied the night before. This time, we'll focus on the theory of making those predictions better. We can initialize the network we built last time and pass in our normalized data x using our forward method and have a look at our estimate of y hat. Right now our predictions are pretty inaccurate. To improve our model, we first need to quantify exactly how wrong our predictions are. We'll do this with a cost function. A cost function allows us to express exactly how wrong or costly our model is given our examples. One way to compute an overall cost is to take each error value, square it, and add these values together. Multiplying by 1/2 will make things simpler down the road. Now that we have a cost, our job is to minimize it. When someone says they're training a network, what they really mean is that they're minimizing a cost function. Our cost is a function of two things: our examples and the weights on our synapses. We don't have much control over our data, so we'll minimize our cost by changing the weights. Conceptually, this is a pretty simple concept. We have a collection of 9 individual weights, and we're saying that there is some combination of w's that will make our cost, j, as small as possible. When I first saw this problem in machine learning, I thought, I'll just try all the weights until I find the best one. After all, I have a computer. Enter the curse of dimensionality. Here's the problem. Let's pretend for a second that we only have one weight instead of 9. To find the ideal value for our weight that will minimize our cost, we need to try a bunch of values for w. Let's say we test 1,000 values. That doesn't seem so bad. After all, my computer is pretty fast. It takes about 0.04 seconds to check 1,000 different weight values for our neural network. Since we've computed the cost for a wide range of values of w, we can just pick the one with the smallest cost, let that be our weight, and now we've trained our network. So you may be thinking that 0.04 seconds to train a network is not so bad, and we haven't even optimized anything yet. Plus, there are other way faster languages than Python out there. Before we optimize though, let's consider the full complexity of the problem. Remember, the 0.04 seconds required is only for one weight, and we have 9 total. Let's next consider 2 weights for a moment. To maintain the same precision, we now need to check 1,000 times 1,000 or 1,000,000 values. This is a lot of work even for a fast computer. After our 1,000,000 evaluations, we found our solution, but it took an agonizing 40 seconds. The real curse of dimensionality kicks in as we continue to add dimensions. Searching through 3 weights would take 1,000,000,000 evaluations, or 11 hours. Searching through all 9 weights we need for our simple neural network would take 1,268,399,679,350,583.5 years. For that reason, the just try everything or brute force optimization method is clearly not going to work. Let's return to the one-dimensional case and see if we can be more clever. Let's evaluate our cost function for a specific value of w. If w is 1.1, for example, we can run our cost function and see that j is 2.8. We haven't learned much yet, but let's try to add a little more information to what we already know. What if we could figure out which way was downhill? If we could, we would know whether to make w smaller or larger to decrease the cost. We could test the cost function immediately to the left and to the right of our test point and see which is smaller. This is called numerical estimation and is sometimes a good approach, but for us there is a better way. Let's look at our equations so far. We have 5 equations, but we can really think of them as one big equation. And since we have one big equation that uniquely determines our cost j from x, y, w1, and w2, we can use our good friend calculus to find exactly what we're looking for. We want to know which way is downhill. That is, what is the rate of change of j with respect to w, also known as the derivative. And in this case, since we're just considering one weight at a time, this is a partial derivative. We can derive an expression for dj/dw that will give us the rate of change of j with respect to w for any value of w. If dj/dw is positive, then the cost function is going uphill. If dj/dw is negative, then the cost function is going downhill. Now we can really speed things up. Since we know in which direction the cost decreases, we can save all the time that we would have spent searching in the wrong direction. We can save even more computational time by iteratively taking steps downhill and stopping when the costs stop getting smaller. This method is known as gradient descent, and although it may not seem so impressive in one dimension, it is capable of incredible speedups in higher dimensions. In fact, in our final video, we'll show that what would have taken 10 to the 27th function evaluations with our brute force method will take less than 100 evaluations with gradient descent. Gradient descent allows us to find needles in very, very, very large haystacks. Now, before we celebrate too much here, there is a restriction. What if our cost function doesn't always go in the same direction? What if it goes up and then back down? The mathematical name for this is non-convex, and it could really throw off our gradient descent algorithm by getting it stuck in a local minimum instead of our ideal global minimum. One of the reasons we chose our cost function to be the sum of squared errors was to exploit the convex nature of quadratic equations. We know that the graph of y equals x squared is a nice convex parabola, and it turns out that higher dimensional versions are too. Another piece of the puzzle here is that depending on how we use our data, it might not matter if our function is convex or not. If we use our examples one at a time instead of all at once, sometimes it won't matter if our function is convex. We will still find a good solution. This is called stochastic gradient descent. So maybe we shouldn't be afraid of non-convex loss functions, as neural network wizard Yann LeCun says in his excellent talk, Who is Afraid of Non-Convex Loss Functions? The details of gradient descent are a deep topic for another day. For now, we're going to do our gradient descent batch style, where we use all our examples at once. And the way we've set up our cost function will keep things nice and time. We decided to use gradient descent to train our neural network so it could make better predictions of your score on a test based on how many hours you slept and how many hours you studied the night before. To perform gradient descent, we need an equation and some code for our gradient, dj/dw. Our weights W are spread across two matrices, W1 and W2. We'll separate our dj/dw computation in the same way, by computing dj/dw1 and dj/dw2 independently. We should have just as many gradient values as weight values, so when we're done, our matrices dj/dw1 and dj/dw2 will be the same size as W1 and W2. Let's work on dj/dw2 first. The sum in our cost function adds the error from each example to create an overall cost. We'll take advantage of the sum rule in differentiation, which says that the derivative of the sums equals the sum of the derivatives. We can move our sigma outside and just worry about the derivative of the inside expression first. To keep things simple, we'll temporarily forget about our summation. Once we've computed dj/dw for a single example, we'll go back and add all our individual derivative terms together. We can now evaluate our first derivative. The power rule tells us to bring down our exponent 2 and multiply. To finish our derivative, we need to apply the chain rule. The chain rule tells us how to take the derivative of a function inside of a function, and generally says that we take the derivative of the outside function and multiply it by the derivative of the inside function. One way to express the chain rule is as the product of derivatives. This will come in very handy as we progress through backpropagation. In fact, a better name for backpropagation might be, don't stop doing the chain rule ever. We've taken the derivative of the outside of our cost function. Now we need to multiply it by the derivative of the inside. Y is just our test scores, which won't change, so the derivative of y, a constant with respect to w, is 0. Y hat, on the other hand, does change with respect to w2, so we'll apply the chain rule and multiply our results by minus dy hat dw2. We now need to think about the derivative of y hat with respect to w2. Equation 4 tells us that y hat is our activation function of z3, so it will be helpful to apply the chain rule again to break dy hat dw2 into dy hat dz3 times dz3 dw2. To find the rate of change of y hat with respect to z3, we need to differentiate our sigmoid activation function with respect to z. Now is a good time to add a new Python method for our derivative of our sigmoid function, sigmoid prime. Our derivative should be largest where our sigmoid function is the steepest, at the value z equals 0. We can now replace dy hat dz3 with f prime of z3. Our final piece of the puzzle is dz3 dw2. This term represents the change of z, our third layer activity, with respect to the weights in the second layer. Z3 is the matrix product of our activities, A2, and our weights, W2. The activities from layer 2 are multiplied by their corresponding weights and added together to yield Z3. If we focus on a single synapse for a moment, we see a simple linear relationship between W and Z, where A is the slope. So for each synapse, dz dw2 is just the activation A on that synapse. Another way to think about what the calculus is doing here is that it is back propagating the error to each weight. By multiplying by the activity on each synapse, the weights that contribute more to the overall error will have larger activations, yield larger djdw2 values, and will be changed more when we perform gradient descent. We need to be careful with our dimensionality here, and if we're clever, we can take care of that summation we got rid of earlier. The first part of our equation, y minus y hat, is of the same dimension as our output data, 3 by 1. F prime of z3 is of the same size, and our first operation is a scalar multiplication. Our resulting 3 by 1 matrix is referred to as the back propagating error, delta 3. We determined that dz3 dw2 is equal to the activity of each synapse. Each value in delta 3 needs to be multiplied by each activity. We can achieve this by transposing A2 and matrix multiplying by delta 3. What's cool here is that the matrix multiplication also takes care of our earlier omission. It adds up the djdw terms across all our examples. Another way to think about what's happening here is that each example our algorithm sees has a certain cost and a certain gradient. The gradient with respect to each example pulls our gradient descent algorithm in a certain direction. It's like every example gets a vote on which way is downhill, and when we perform batch gradient descent, we just add together everyone's vote, call it downhill, and move in that direction. We'll code up our gradients in Python in a new method, cost function prime. NumPy's multiply method performs element-wise multiplication, and the dot method performs matrix multiplication. We now have one final term to compute, djdw1. The derivation begins the same way as before by computing the derivative through our final layer. First dj dy hat, then dy hat dz3. We now take the derivative across our synapses, which is a little different from our job last time, which was computing the derivative with respect to the weights on our synapses. There's still a nice linear relationship along each synapse, but now we're interested in the rate of change of z3 with respect to A2. Now the slope is just equal to the weight value for that synapse. We can achieve this mathematically by multiplying by W2 transpose. Our next term to work on is dA2 dz2. This step is just like the derivative across our layer 3 neurons, so we can just multiply by f prime of z2. Our final computation here is dz2 dw1. This is very similar to our dz3 dw2 computation. There is a simple linear relationship on the synapses between z and w1. In this case, though, the slope is the input value x. We can use the same technique as last time and multiply by x transpose, effectively applying the derivative and adding our djdw1s together across all our examples. All that's left is to code this equation in Python. What's cool here is that if we want to make a deeper neural network, we could just stack a bunch of these operations together. So how should we change our w's to decrease our cost? We can now compute djdw, which tells us which way is uphill in our 9-dimensional optimization space. If we move this way by adding a scalar times our derivative to all of our weights, our cost will increase. And if we do the opposite, subtract our gradient from our weights, we will move downhill and reduce our cost. This simple step downhill is the core of gradient descent and a key part of how even very sophisticated learning.
Got all that? Easy, right? No problem. Just walk in the park. So, What you should do now, if you're not too familiar with linear algebra, is consider taking the best course on the planet, which is MIT 1806, Linear Algebra, given by God himself, no one other than Gilbert Strang. I've been through this, read through the book, some of it, and it is quite a piece of work, but it's good to go through all the basic stuff, even though it's kind of used off the cuff in neural networks. Now this is the jewel in the crown. If you really want to get to the bottom of understanding the complexities, depth and breadth of neural networks, you must, without any shadow of a doubt, expend a lot of time going through this course. Stanford course CS231, which was pretty much invented, presented by Andrew Carpathy himself. If you don't know who he is, go to my YouTube channel, Altcoin Express, wander down and look at these two parts. Part 1, Andrew Carpathy Part 1, Part 2, Andrew Carpathy Part 2. I recommend you go through these anyway. Guy's a genius. He now works for Tesla as Director of Artificial Intelligence for Elon Musk. Preemptive to that, he worked, after he graduated and did this course, he worked at OpenAI, which was the institute that Elon Musk helped instigate, which is a kind of a autonomous breeding ground for AI research. So watch those and go over to the course and go through the course. He teaches about 80% of this course with a helper. It is quite detailed. There's a staggering amount underneath the hood of this lot. You need to go through it all. Take time. And if you didn't get the math, well, I had to spend quite a lot of effort putting this on paper. So, just to help you out, since I'm a nice guy, where are we? Here is the math. Relative to that seminar that was just given. So I'll leave this on the screen for a while, so you've got a chance to just screen print, dump it into Paint, print it out, and I've spent a lot of time doing this. It's very, very difficult to find out how to get this onto print. So that's page 1. It all relates to the algorithm, and I'll go into the code shortly. I'll put some of the code up. So where's page 2? So here's page 2. All this hard work is done for you. It took me hours to do this, not to mention getting my head around all of this shit. But once you've done it, and you've got to go through that CS231 course, it's invaluable. It is the 101 how to do neural networks. It goes through so much of the machinery involved in all this lot. You'll learn a tremendous amount, and you've got to do a lot of work as well. And 3, and that's the final. You should be able to relate this to the equations. Give you time to get through that, and I'll go onto my code. So I put this up in the last presentation. I started off getting house values, prices and features, which is the area of the land plot against house prices from Zillow in my local area. And here's your differentiated sigma prime, sigmoid function sigma prime. We don't use sigma functions anymore. We use tan or ReLU, but that will come up somewhere else, and I've got other stuff that you can use. So here is this back propagation code, this little bit here, and that's what all the math has to do with. And thereafterwards, the rest of the seminar that comes down the road from this, some of this I couldn't understand, and pretty much had to work it out for myself, and I'll show you the rest of this code later on. But for now, just get into the math, try and get your head around it. Do this, the convolutional neural networks computer vision course, and if you can get through the Gilbert-Strand course, there's enough to keep you busy there for more than a few weeks. So that is it in a nutshell. And next time round, we'll continue with this when people have had enough time to absorb some of this.